Okay, people joining this live stream. Well, I'm kind of letting you in on my Tuesday afternoon activity here. Of doing some science, kind of more or less by myself, um, exploring some things that I've been exploring recently. Let me just set something up here which wasn't working correctly. Hold on 1 second here. I just need to set something up. Okay. All right. I am going to be exploring these things called combinators, which are part of my program of trying to get intuition that's relevant for our physics project. And also, there's kind of an interesting historical tie-in because December 7th, 1920 was the origination of combinators, which is almost exactly 100 years ago. So I've been exploring these things. So let me give you an example. So combinators are a foundation for computation. They are based on these rules here. And what happens with them is given a particular expression like this, for example, one can apply those rules. Let's say we apply rules to this one 10 times. Okay, after a limited number of steps, based on applying these rules, we get just the constant S. And the whole point of combinators is that there exists an arrangement of S's and K's so that you can implement any function or any lambda expression. Okay, now what I've been looking at is for 100 years, we've known that S and K together are universal. What I've been interested in is looking just at the behavior of S itself. And I can show you, I'll show you a few examples, just a lot of wild things that happen. Let me show you something here. Let's just pick out, there's a good example here. Yeah, let me pick out these here. So I've got a few examples of interesting combinators. These are just expressions that involve 8 things here, and these have the feature that they don't die out, at least not for a while. So let's try looking here at just looking at the leaf count, that is the number of symbols that appear in each of these. So in these particular cases, if I just say leaf count of non-ter, and they're all 8. There are 8 symbols that occur here. So let me go ahead and say I'm going to use some functions I wrote. Okay, I'm going to do this. I'm going to say grow them up until size 2000, and then I'm going to use this non-terms thing, and then I'm going to say for each of those, list step plot of those. And actually, why don't I go ahead and say plot label. Plot label is the actual combinator. And then what I want to do is I want to say, I want to run this in parallel across my little network of computers. All right, let's take a look at what this gives. So this is now running, hopefully. I have to start up my computers. It should run all of these kind of curated collection of creatures. Oh boy, why is that happening? That shouldn't happen. That was supposed to have just been fixed, actually. Chapin screenshot.
Yes, got it. Oh.
Okay, thanks. Oh my. That's disastrous. Okay, please ask Roger to, oh dear. This is not going to be any fun. This is, I'm running the very latest version, And oh boy, he got something wrong here.
Can you send me that notebook once it's done running?
It will not be
This
done
will...
running. It will die. So
Okay, I've got screenshots, so.
I think we should get Roger on this thing, please.
Okay, I'm grabbing him.
Yeah, this is going to be no fun if we can't get this to work. Bad, bad, bad. Okay, in any case, what I was going to try to show, let me cheat and just show the answer while we wait. Here, what I was going to show you was, this is for all those different combinator expressions. This shows the growth in size as we progressively run it. And what you see is some of them, they grow, and then they die off again. Other ones, they grow, and we can readily see that they're going to repeat. Other ones, they grow, but we can't really tell what's going to happen. And so I wanted to explore some of those we can't really tell what's going to happen cases. Let me go ahead. I've got another way to do this, I think. I can't believe this failed. This is just very frustrating. Very, very, very frustrating. Okay, well, let me just I'm going to send you this notebook just so this can be separately run.
Thank you.
Okay, I'm gonna get to some things which I can do even without this. Okay, so let me show you. If I look at all possible combinator expressions, the very first one that doesn't just die out is this one here. So if I say skvolve list of this, and I say run for 30 steps, for example. Oops, I need to run something else here. Okay, it's going to make these very complicated expressions, and I can say, show me the leaf count for these, and you'll see that it grows like that. If I say list log plot of that joined as true, it'll give me, okay, so that's interesting. So that's it's not exponentially growing. So we can go and that's interesting. So the thing is on an exponential scale, it's not. So we don't actually know for sure that this is going to go on forever. So let's try to figure out. Whoever's not on mute should get on mute. Hello.
Sorry, that was Roger that joined.
Are you not, Roger? Are you here?
Yeah, I'm here.
So this parallel kernel thing has failed completely. Can we get this fixed or not?
Yeah, let me take a look at it.
Well, that's what I was hoping you would be doing. Okay, why don't you go on mute and let me know when you've had a chance to look at it. Okay, so one of the questions is, can we understand the fact that this seems to be growing, and can we prove that it will always grow or not? to get a sense of what's actually happening here, we can look at the actual expressions that we get out. And let's just see. They're big, complicated messes. Actually, I think these may be ridiculously complicated as well. No, okay. So these are expression trees that correspond to these things. Again, not particularly simple. Now, I think one thing we might want to do is to look at, yeah, here's what I want to do. I want to say, the way that I'm updating this, I'm using these rules, but there are many different possible ways that these rules could be applied. It's much like in the physics project, there are many different possible rule applications. And what I'm doing here is using a particular rule application. So let's take a look at how that works. So let's look here. We've got all these results. And for each one of these, we're going to ask the question, what is the, okay, so we're going to say position in each of these of S of blank, a blank, a blank, and let's take a look at that. So this is showing me all the possible places where that rule could be applied. So if I look at that in a column, that's showing me on the first step, so that nothing there means it's going to apply to the whole expression. So this is showing me for each step, what are all the possible places where the rule could be applied. Now, the particular way that I'm making the pictures above, I have a particular way of choosing which position to use. I'm sorting those positions, shortest first. I'm taking the first of those sorted positions. So here, I'll get those results, and this will be the actual position of the thing that I'm that I'm applying the rule to. So this is kind of interesting to look at where is the rule getting applied. So let's do that for 50 steps. Let's ask the question, can we see something about where the rule is getting applied? It's a little bit unclear. That's interesting. I mean, if we look at the lengths of each of these, that's telling us sort of where the rule application is happening. Let's see if we can get that to 100 steps. And this is effective. I guess this is telling us the depth at which the rule is being applied. So it's telling us how far down in the expression we're going. Let's see if we can get it to 100 here. Not sure if we'll be able to. Yes, we can. What did I do wrong here? I need to do this. Okay, let's look at that. Okay, I don't know what that's telling us necessarily, but that's telling us the depth in the expression at which the rule application is happening. I wonder if we can get it to 200. I wonder what this will. And we can also show, actually, an interesting thing to compare to this would be to compare the actual overall depth of the expression. So let's take a look at that. So this is asking for each of those. So let's do this. Let's say length of this thing here, as well as leaf count of the whole expression and the length of each thing applied to that. And then let's say a list step plot of transpose of that. And that should give us, oh boy. Oh, I didn't want leaf count. I wanted depth there. Okay, so this is kind of interesting. So that's showing us the depth, the overall depth of the expression, together with the depth of the place where the actual rewrite got done. Okay, so the next question is, let's look at the actual expressions that were being rewritten and see whether we can understand how those work. So there, what we want to do is we want to say, okay, so we want to take this and want to take that thing and we want to say extract in the expression. Let's try saying this. So this is now going to be the actual expression that was getting rewritten. So it should be S of blank, 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 blank. Okay. So this is now showing us. So maybe what we can do is, let's do this. I'm just curious what happens if we do this. We say x blank. No, let's take that. Okay, so let's go, let's say 30 steps. So these are all of the expressions that are getting rewritten. So now I'm curious if I show, and I think Mano was here. Maybe Mano has a better version of combinator tree now. But this is, okay. So one question we can ask ourselves, oh, that's goofy, is there some regularity to these trees? Can we see that the same tree is showing up over and over again, which would suggest that we'll keep going in doing this rewrite? So I'm not seeing that in any particularly obvious way here, that these trees, but let's try breaking this up again in a certain way. So let's try for each of these, let's say first of extract of that. Okay, so now let's say for each of those, let's say slash dot s of x of y of z arrow x, y, z. And so now that's going to give us, so now here we can say map combinator tree and this at level 2. So what that should do is it should give us a bunch of separate trees. Boy, this is hard to understand. That's really weird. So what this is saying is there's a single letter S here. Boy, that's odd. That's really odd. Well, let's find in there position in this of S at level 2. Did I do the right thing? Maybe it's level 3 I want to do here. Ag. Line 74. Position in line 74 of S at level 3, I think. Okay, there we go. So that's showing us I'm a little confused by this. I'm trying to find the things where those individual S's. Oh, there we go. There they are. So those are the individual S's that occur. And I'm curious whether if we plot that, let's see. So let's just keep running this a while longer. 974. Let's run this for 100 steps, for example. And now I want to find out whether these S's that appear, whether there is some regularity to these. So I'm trying to find out. Let's go ahead. Let's just say list plot of this. Whew, nothing very obvious there. Okay. This is trying to find out whether this thing is going to kind of keep generating itself over and over again by kind of having a sort of a generator object that it keeps on finding in the expression. So let's look at, okay, so let's do the following. Let's say first slash at %80, and then let's say differences of that. Oh my gosh, this is a complicated creature. You know, I've been doing this for so many years. How can I, you know, it's like this is such a simple system. I mean, we just started off from this S of S of S thing here, and it's making all this stuff. How do we understand this? Okay, so the question before us is, will this keep going forever, or will it eventually terminate? And can we prove that it will keep going forever? And one way to prove that it will keep going forever is to show that in some sense, some aspect of what's being rewritten is repeating forever. But that is not obviously happening here. I mean, this is a big mess. I don't see any repetition in this at all. Boy, this is hard to understand. All right, let's see what we can analyze here. So let me show you another thing. Maybe that will help. Maybe it won't. I'm not sure. Okay. So one thing I should explain is this is based on rewriting that combinator expression, applying that rule S of X blank, Y blank, Z blank goes to whatever, applying it at a particular position. But there are different positions we could apply it at, and there is a good, we have a function called multi-way combinator, which will do that. So if I say multi-way combinator of SK rules, and then I say that initial condition there, and I say, I don't want to live too dangerously here, I say like 5 steps, and then I say states graph, this will show me, oh, what a mess. Okay, let's say 10. Let's say 13. Okay, here we go. So this is showing me all possible rewrites. So for a long time, it's unique. And then suddenly at step 11 or something, there start to be 2 possible rewrites. Now remember, we are picking a particular rewrite, a particular path through this graph that was based on our leftmost, outermost evaluation, was based on that particular sorting of the positions at which rewrites can occur. Okay, let's keep going with this graph. Let's see what it does. Okay, so remember so let's go to 15 steps and let's just show the structure of the graph. Okay, so there's our stem, and then it goes into this complicated mess here. And what I think is the case, let's see if we go to 17 steps, it's getting more complicated. And I think if we simply ask how many different states do we get to, how many distinct states do we get to after a certain number of steps, let's take a look at that function there. So let's just say length of that. Okay, so this is a very rapidly growing thing. Let's see if we can get it to, let's see if we can live dangerously and get it to 19. Oh boy. Even 19 is difficult. So I don't know whether this is growing, maybe even growing more than exponentially. I'm not sure. Well, let's see. Humph. Well, let's kill that. Let's see whether we can get it to 18 at least. We're waiting. So, okay, let's take a look at the ratios there. So that's interesting. The ratios are increasing. So I'm not super surprised by that, because what's happening is that the average length of these things is increasing. So let's take a look here at, for each of these, let's look at the leaf count of 2 expression. Let's do this, map that onto level 2. I think that's right. And now, my God, why is that taking so long? Maybe we should do one. Well, okay, we got that. Okay, so now let's say histogram. It's got to be very interesting for the first few steps there. So let's just go, well, it's 1, 2, 3, 4, 5, 6, 7, 8. Let's say take that -8, and let's map histogram over that. And okay, there we go. Okay, so this is showing the distribution of lengths of objects that we get, distribution of sizes of objects. So what this is saying is that by length, by step 18, the typical object is of length 300 or something, or length. So let's look at how in that collection there, let's look at the mean length. Percent. Well, we can just go ahead and say %94, and then numerical value. Okay, so this is saying how the mean length of the object increases with step number. And what this is telling us is, if I do a list line plot, this is why we're seeing faster than exponential growth, because there are more and more places where you can do a rewrite. So there are more and more, not only is, so if there were a fixed number of places, we could try rewriting in all possible ways, but there are an increasing number of places where the rewrite can happen. So if I say ratios 96, I can say, let's see whether that ratio is increasing. Okay, that ratio is a mess, but maybe it's converging to something like 1.2. So that would mean that the length of the average length is exponentially increasing. And so that means that the total size of the multi-way graph could double exponentially increase. So let's go ahead. What we're trying to understand is, can this ever terminate? Okay, can we ever reach a place where, and one, there's a theorem that says that if it's going to terminate, this leftmost, outermost approach will lead to termination. So that approach that we were trying before, of looking at just this particular rewrite, it will terminate if it's going to terminate. And sometimes they can take, I found ones that take thousands of steps to terminate. Maybe this one takes 10 to the 10 to the 100 steps to terminate. And that's not such a crazy idea, because I did find an example in the NKS book of something similar to this. I'll show you it, where it takes a shockingly long time to terminate. This is not quite a combinator system. It's a generalization of a combinator system. It's a system where instead of the specific S combinator, we have a different rule here. And this system has the feature that it takes, well, with n initial values, it takes 2 to the 2 to the 2 n times steps to terminate. So it's the power tower of n steps that it takes to terminate. So a really long time. So there are things like that running around here. And actually, I'm curious whether we should be able to turn this thing into a combinator. Let's actually do that. So this thing is x of x of y. So let me see if I can do that. Let's actually turn that into a combinator. So we should be able to do that by saying, okay, let's say tetration symbolic system, and we're saying two SK combinators of x of x of y So that's the individual combinator expression. And now it's a little bit ornate because we have to use the fixed point combinator, the y combinator, to keep applying this to the to a particular thing. So if we use that combinator and we say, let's apply that particular combinator, let's apply that to AB, and then let's say SK fixed point evolve list, that thing should grind around for a while and then give the result A of B, which is exactly what we would expect. But the question now is, can we make something which will be an iteration, a nest of this? Mano, do you happen to have the curated combinators, including the Y combinator? Do you have the expression for the Y combinator?
I can pull it up. Do you have axiomatic theory? It should be in there, but in the, you know, quantified form and all.
Combinator axioms. Okay, where do I go to find it? If I just say combinator axioms.
Yeah, so the Y Combinator is the last one, but you would need to get it in the nested bracket form, I guess.
But that's an implicit equation for the Y Combinator. That's an equation form of the Y Combinator. I need the resolved form of the Y Combinator. That's very beautiful, by the way. When are we going to get the new symbol for the application?
I'm not sure yet. Jose and Roman would probably know.
Unfortunately, when I look up Y Combinator on the web to just find the form of the Y Combinator, all I find is Paul Graham's organization. I bet if I look up fixed point combinator, I'll have a better chance.
So you want it in SK form because I found it.
Okay, can you put it in the chat, please?
There it is.
Oh, how do we translate that into non-ridiculous parenthesized form? Oh gosh, I can't do this and get it right. Can you try and do this of just taking the, but then it should be the case that if I take that combinator, and then so if I'm correct, I take the Y combinator, I apply it to this combinator here, actually, I'm not sure in which order I apply it. What are the arguments of the Y combinator? Is it the function and then, oh, here it is. Y combinator of this applied to that. Is that the right way round? See, I want something where I can say Y of that thing applied to XPA, and then I want that to resolve, so to speak.
Resolve into
nested application of this combinator expression, I think. I'm not sure if this is quite going to work like this. All right, I think this is a separate problem. Let's not go down that. Let's just look at the S combinator case. Maybe somebody in the chat knows how to do this. Yes, Richard is commenting. It's like the Hyder in Goodstein's theorem. I think there will be a I think we are at 125%. I'll go to 150% here, but I want to keep enough stuff on the screen, so otherwise it's hard for me to work on things. All right, so what we want to learn here is how can we prove that the S combinator, that this expression is never going to terminate? Can we prove non-termination? I think this is provable. I think this actually was proved. We probably look it up. I'm now somewhat motivated to look up the proof of the non-termination of this particular S combinator expression. Let me just see if I can find something here. I think I had okay, this is a paper about the S combinator, and that's not useful. I was saying there exists an infinite, actually that's an interesting claim, that SSS, I don't believe that claim actually. That was a claim that SSS on its own has an infinite path. So that would be the claim that SSS, let's not live too dangerously, let's just do 10 steps. I don't believe it. So the question is, does this yes. I'm just thinking about this. Which one is this one? The titration one? X of X of Y. Okay. All right. Well, there's a claim that I don't understand this proof. I don't understand this proof at all. And there's a more recent claim. Let me see if I can pull it up. Oh, for goodness sake. I thought there was a nice paper called Dance of the Starlings. And I thought that might be turns out there's a Dance of the Starlings that has something to do with actual birds, as opposed to the S Combinator, which is okay. So let's see. My gosh. Claim by induction. So I wonder whether we can use automated theorem proving to prove this. From these clauses, it follows there's an infinite reduction. Okay, well, let's test that. S of S of S. That is otherwise known as S of 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 S. Okay. Okay, so the claim is that this one has an infinite. So it's looking plausible. That's infinite. How many steps does that have? And how many leaves does that? Oh, it has 9 leaves. I haven't looked at the 9-leaf ones yet myself. Okay, so this claims. Okay, so this claims it goes like that. So the claim is, what the heck is this? Contains an infinite number of steps, consequently infinite. So this is essentially an algebraic notation for this object. And this is saying that there's a way of representing the successive steps here as some algebraic form that we can then prove doesn't terminate. Okay, so this is an attempt to show how it's an attempt to show that there are pieces. So this is an attempt, I think, to represent something which will be a repeating part of, boy, the main lesson of this whole thing is, things that look simple don't end up being simple. Oh, Richard on our live stream says he did manage to compile that generalized hyperoperation to SK. Hey, if you've got an SK expression that does it, just send it to us. I'd like to see it. Okay, so I want to come back here and I want to try and get a methodology for understanding how, what is it that's repeating here? What is the, can we understand something about the structure and does it repeat? So I'm a little bit hopeful that we will be able to see something in, so this is saying, this is asking the question. You see, I do think that this is going to end up being that the top levels of these trees are going to repeat in some way. How to think about this? Okay, let's take a look here. So these are the things that are getting rewritten. So I'm going to try to look at whether, let's look at just the top few levels of those trees. How would we get that? We would say below a certain level. Okay, so let's say top of tree of an expression. And what I'm proposing to do is to say map of x onto expression. Actually, let's say level. Map that onto this at level lev through -1. See if this works. So my theory is that I take some random complicated expression here. Let's say I take these ones here because those are the ones I want. And, oh, here we go. So let's say these are E30 or something, the 30 of these. And let's say I just say, let's say last of E30, it'll be a big complicated mess. And now I say top of tree, percent comma 1. Top of tree. Oh, actually, I don't want to do that. I'm sorry. I don't want this part. Okay, so is this right? My God, this is confusing. Okay, so let's say we say tree form of %113. Heads goes to, oh, it doesn't have a heads option. I want to say function to applications, to application of %113, and then I want to say tree form. Okay, so that is the tree that corresponds to this. And what I'm saying is I want beyond level 1, I want to cut it off and I want all those subtrees removed. So what I'm saying here, is this right? Can anybody see, is this right? I'm saying map this at, well, here, I can test it by saying, I take this expression and I say, map onto this expression f at levels 2 through -1. Heads goes to true. Oh my gosh, this is hard to understand. My gosh. Well, I don't really understand this. What I'm trying to do is I'm trying to, below a certain level in this tree. Well, okay, here's a hacky way to do it. I don't like it at all. Okay, I'm going to say map indexed of if length of hash 2 is greater than 3, let's say, then just x, otherwise hash 1. And let's go here See what that looks like. Yeah, so that should... What happened here? What happened here? Oh, I see what I have to do. Okay. So, let's see. Okay, we're looking at, Richard has sent various things here where, okay. Richard is correctly distracting me by talking about Goodstein functions and Goodstein sequences, and I'm just for sort of purposes of reminding about things. I know let's see, Goodstein sequences and unprovability. So Goodstein sequences, I have to remember how this works. Goodstein was one of the very few students of Wittgenstein, as I remember correctly. Boy, okay, there's progress in the world of Goodstein sequences. They were pretty obscure back when I looked at them and working on the NKS book. That's really kind of fun. I mean, Goodstein sequences are highly related to things like transfinite numbers and a lot of other elaborate things. And I'm going to guess that there's a relationship between transfinite numbers and these infinite combinator trees. And that's part of one of the things I wanted to investigate. But okay, this successfully truncated my tree. Okay, so it may not be the most efficient way to do it, but it does seem to be a way that successfully does it. I'm not quite sure why my other thing didn't work, but let's rewrite top of tree to okay, so top of tree. Why is this doing x of x here? Why does it do that? I don't understand that. This should be a fixed level that this is going to. So top of tree. So it says here, that would be this. And let's say we're going to have a stub, default it to x. And that's the stub there. And then greater than lev. And then this is expa. Okay, so let's say top of tree of this thing here. And I think what's going to happen is, let's say I say level 1. Okay, now what is the depth of that? The depth of that is 2. So I think I'm off by 1 here. Oh gosh. Ho, 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 ho. Why did that thing not get stubbed? Why did that S there not turn into a stub? So if map indexed, if length of hash 2 is greater than lev, turn it into a stub. So at this position here, that is, oh, oh, it's because of asymmetry between heads and other things. It's not a big deal. Okay, so that's that stub. So if we go a little bit deeper, the depth of that better be 3. It is. Okay, so we're able to successfully stub these things. We're able to successfully find these stubs. Okay, so now let's take our E30 expression. Let's repeat it again. And I want to get the stubs, the top of the trees for this. So let's say top of tree. Oh, for goodness sake. What a complicated mess. Okay, let's just check. Oh my gosh. They're all depth 2. I know the problem. I know the problem. The problem is that depth, let me just check something. F of x of x of y of z of a, what is the depth of that? Wait a minute. Let's try zw. Okay, it's not accounting for the head in computing the depth. So what we need to do here okay, this is going to be a little trickier. We need to convert this expression to, we need to say function to application of this. And we say top of tree of that. I think I have a different definition here, clear top of tree. Okay, that's better. So now I want to convert that back again, and to get from an application, what do? I just have to replace the application by the first argument. I think I just have to take this / dot application of x blank y blank goes to x of y. I think that's right. Okay. All right, so let's try taking this thing here. Okay, so at the very, very top level, somewhat surprisingly, and actually incomprehensibly, and it doesn't seem right, something is wrong here. Mano, can you see what's going on? So in this case, if we take the first 3 elements of E30, 4 elements of E30, this is showing us each one of these things is of the form S of S of S of S of S. It's got S of S of S because it's got to match this pattern here. So how can our tree, how can our thing that's trying to cut off a particular level in the tree end up not having that same form? So that's the thing with application.
Is there a place where I can access this notebook?
Yeah, it's in the usual place.
Okay, let me look.
Okay, so that's the usual. Well, look, what I'm trying to do is I'm trying to get what is the structure of the top of these trees, and do they have any uniformity to them? And then my next question is, what if I look at all the S things that eventually blow up, do they all go through a common? Is there a piece to them that is sort of the generator of the blow up, and is it always the same? And is the blow up that they generate always of the same structure? Can it be represented by the same essentially transfinite number that corresponds to that infinite tree? Well, let's see. Maybe what I can do, while Mano is trying to figure this out, I'm going to look at something else. I'm going to look at additional more S forms. Okay, so what I had previously, so if I say groupings of S table S7, that was the minimal case that I construct arrow 2. That's giving me all possible S of S things, and only one of these blows up. So if I say, but I have to find out. Yeah, so if I say sk evolve list of hash, and I say select that, comma 10, let's say, I'll try and make a filtering for which ones of these are blowing up. So this is greater than, let's say, 20. I don't know whether that's going to be a good thing. None. Okay. Oh, whoops. I meant leaf count. Oh, boy. Okay. So what I want to do, obviously, is to say, after 10 steps, right. So to filter these, what I want to do is I want to say, okay, here's my idea. Let's say leaf count of that. Let's go up to, like, say, 20 steps. And then let's map it over this. And then let's say at each step, so let's transpose that. And at each step, what's the histogram of leaf counts that have been achieved? Okay, so what this is saying is, and let's actually do the following thing. Let's say hash, comma 1, and then let's say plot range to all. Okay, so this is saying, and actually what I probably want to do is a log counts there. Really? Thought that worked. See, histogram. Maybe it has to be like this. I'm surprised by that. Seems wrong to me, but let's see whether that works. Yes, it does work. Okay, so what this is saying is, if I look at the distribution of the lengths reached, what I see is that there are a limited number here that seem to break away from the pack. And presumably those are going to be the ones that are not going to terminate. And although I could just ask how many have terminated by a particular step, but I'm going to try doing this for the case of the 8. Okay, so now I'm going to say this, and let me do these in parallel, and let's hope this now works. All right, let's try starting up my machines again. Okay, so that's now showing us, oh boy, this is a more complicated story. Look at that. See, it's not so obvious which ones of these are going to be long-time survivors and which ones of them are just going to die off. Wonder if we can run it a few more steps. Let's see whether it works to run it for 25 steps. This may be a super bad idea. Okay. Okay, so we have some that are like really taking off there with 1400 and others that are not as taking off. But let's also see whether which ones have reached fixed points. So if we make, okay, so really what we want to test is, actually I've got a good way to test this. Okay, here we go. Yes, I've actually got a good idea here. Okay, so what I'm going to do is I'm going to say fixed point sk fixed point evolve list of this thing here. And I'm going to limit that to, let's say, 2000, leaf count of 2000. And then I'm going to say, let's say, sk terminated of expr is, I wonder if matchq has a, no, actually I could do this. I could say count of in expr of s of blank, a blank, a blank, or k of blank, a blank, 0 infinity, heads goes to true. What that's going to do is it's going to tell me, let's see, that's counting the number of these. And so then if I say that's equal to 0, it will tell me that it is terminated. So what that means is if I say sk terminated of s of k, it should tell me it's terminated. If I say that of k of s, it will say false, it's not terminated. I like that function. Okay, so that is a termination tester for whether there is another step that I could take. Let me just add that to something here. Okay, so now, let's see. So what I want to do is I want to say up to this, I want to say select in this groupings thing for all sk forms for which, actually, let me just go ahead and do this. Let's say, see, where's my sk? Okay, I need to change a little bit of code here. Let's see if this is right. Okay, now I should be able to say sk fixed point evolve list. And let me say something like hash 2000, 2000. And then let me say sk terminated. Let's say not that, and let me say select of, well, let's just do the 7 case because we know there should be 2 answers to that. Oh, splat. Why did it do that? Okay, so let's take one of those and let's say SK fixed point evolve list of this. Oh, I know what the problem is. That's what I want to change. Okay, that's not encouraging. Okay, so let's try then the one that we had, which didn't terminate, which is this one here. Okay, that makes a big messy thing. And now we say SK terminated of that. It's false that it terminated. So I should be able to say, that grouping isn't wrong, is it? I'm very confused. I take this. Okay, how big is that one? Oh, that one is longer. Okay, I need to take the one that's actually the right size. That's this one here. I'm very confused here. What's going on? Oh, that open bracket, close bracket is super wrong. Well, let's do this. And let's say the last element of that. That's better. Okay, so that doesn't seem right. I must have made a mistake in that form there. Well, we can do this. It's not the most efficient way to do it, but we can do this. Okay, so then last. There we go. Very good. So those are the two non-terminating cases for size 7. Okay, so let's look at size 8. Okay, how many non-terminating cases are there? 41. Okay, let's see if we believe that these are non-terminating. So let's say we do this. We compute this thing, and we say leaf count of that, and then we say list line plot of that, and then we say map that over %169. Okay. Like, this is horrifying because it's like, are they going to go on going up forever, or are they going to crash and come down? Like this one here, is it going to go up forever, or is it going to crash and come down? So that's the first one here. So let's try to explore that one, and let's see whether undecidability has bitten us, unresolvedly bitten us. So let's take this, and let's look at that, and let's say we go. And then we need to figure out, is there some way that we can prove that this one doesn't terminate? Okay, let's go up a little bit in this. So that goes up to, let's go to 5,000 here. Okay, it certainly doesn't look like it's terminating, but let's see whether if we do a list line plot of this. Oh my gosh. These things are just crazy. Like, how do we know whether this thing is going to keep going up or whether it's going to crash and come down? Like, how do we prove that? Let's try just seeing whether we can get to, I don't know if we can. Let's see if we can get to 25,000 here. Okay, it's going up roughly linearly, but how do we prove that? How do we show that this is not going to terminate? Let's try looking at one more thing. Let's try looking at the non-terminators for size 9, and let's see whether they're all looking similar to this. Because these are all... Okay, size 9 non-terminators. I maybe should do this with parallel computation. No, I managed to get it. Okay. Let's say the length of that. 276. Okay, so let's go ahead and make pictures of them all. And now we need to have... Let's go this. Let's make a function, resource function of, I have an interactive selector, list selector of this thing, arrow, the combinator, map that onto percent. Actually, let me go ahead and do map that onto line 176. But actually, I want to check one thing first. I want to check that we're actually correctly parallel computing this. Oh, looks good. Okay. All right, parallel map monitored of this thing, resource function of that. Okay, and now we want to say on that interactive list selector. Okay, here goes. All right, and actually I can make these small. Let me not make them very big. I don't need to make them big. Image size tiny. Okay, here goes. Okay. All right, so now our question is, are there any surprises in this collection of creatures? Are there any that look qualitatively different? So I'm a little bit interested in these ones that have little scallops in them. I don't know, story of my life is basically the zoology of looking through tables like this over and over and over again. Okay, that one is different. That one is different. Hard to believe it's the only one like that. All the others seem roughly linear. Let's take a look at that one. Okay, there's that one. Okay, so let's go ahead and say, let's take that thing there. I'm going to maybe, I mean, I may be wrong that this one is any different. We'll find out in a moment. It is not the same. It is not the same. There's something different going on here. So let's take a look at this guy, and let's say ratios of that. Oh boy, 1.08. Let's just look at that. Weird. Weird, weird, weird. All right, let's take this up to 10,000. Let's take up to 25,000. Should survive. Oh, no, 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 no. Not, oh my God, I managed to get there. Wowee. Well. Okay, what is that doing? What is it doing? It's crazy. So I mean, that's sort of scalloping down to an asymptote that I bet is not equal to 1. Maybe it is, but I don't think it is. I'm going to guess that this is asymptotic to some value. I mean, let's go ahead and get the minima there. We'll what we want to do here is find the peaks in this, right? So find peaks. How do we find the minimum peaks? So I guess we can just say find peaks of the negative of %186. Okay, so that's finding the position of those minima. And if I say, so I can go ahead and I can just say list line plot of this, and that should give me the thing asymptoting to something. Now, maybe that's going to asymptote to 1, but I don't think it is. I think it's going to asymptote to 1.03 something or other. Question is, what on earth is that constant when it's asymptoting to yeah, so the question is, okay, so that one looks weird, but let's take a look at some of these others, because I want to kind of look at, let's, instead of plotting this, let's go ahead and plot the ratios and see whether that shows us anything interesting. Because the ratios of these ones that seem like they're more or less constant would be, okay, so let's say ratios of this. Boy. Okay, a little bit more structure here. But this is, okay, so most of these, curiously, are going very, very, very close to 1 quite quickly. There's some excursions away from 1. Most of them are going really close to 1. You know what I want to do? I want to say here in this list line plot, I want to say plot range arrow automatic for the x-axis, and I want to go 1.0 to automatic to up there, so that I make sure that I'm plotting down to 1 for all of them. So let's go ahead and run it. It's interesting when there's one of these that, here, I'm just going to make these a bit bigger. Let's make them 200. Okay. Okay, so a lot of them kind of die like this, but I wonder whether they stay dead. Kind of have a feeling I should run. Okay, so there's a lot that, okay, there's things like that. Question is whether this thing comes back to life again, or whether it just stays at size 1 forever, at ratio 1 forever. Okay, let's look. So there are these ones that are gradually going down. There are these ones that just sort of go splat. And there are some that have a little, oh boy, that's a weird creature. Notice that the X scales are different because I had a cutoff on the size of the object that's being produced. So let's see if we see whether that guy that we found previously sticks out a lot. Yes, there it is. It doesn't go down to 1. Now, we could also look at the histogram. Well, actually, that was what I thought I was looking at there. Let's see. I'm very confused by these. That one is nice and regular, at least. Let's look at what that one is. Oh, boy. Oh, that was our previous guy that didn't go down to 1. I just want to get a sense. Okay, so those are ratios there. Let's see, what else can we look at here that gives us a sense of whether these things are going to, I mean, I can certainly run them longer. I guess I can run them longer, and I can ask, why don't I plot let's say just between 1 and 1.05. No, 1.15, for example. And let me run them for, let's say, 10,000 steps, since it seemed to be going quite quickly. Okay, so these are now all on the same scale. But although their X scales may be different. Okay, so what's going on here? Okay, there's a lot of stuff that just sort of dies down. Okay, that's one that erupts again. I want to look at that one some more. That one has lots of eruptions. So does that one, but it looks like it's the same guy. Yeah, these ones with eruptions, I'm kind of interested in. I think those may have some different behavior. That one seems to have kind of a whole sequence of those things. That one is erupting all over the place. Ah, there is our sticking out like a sore thumb. Well, I'm going to go through and look at that one again, because that one I think is just a very different type of behavior. Yeah, that one is interesting too. I'm going to go back and pick up those again. Okay, so let's copy these. These are random eruptions. And then we've got this guy here, together with that one there. Okay, so these are, actually the middle ones are, so those two seem like they're larger scale growth. And this one here is highly regular. I want to look at this one because I just have a suspicion that that one might be easy to understand. So let's give it a try. So let's say this one here, let's just say SK fixed point evolve list of this thing. Okay, let's look at ratios of those. Okay, now let's look at, I'm going to look at that minus 1, and then I'm going to say 1 over that, and then I'm going to list line plot that. Oh, fancy that. A straight line. Okay, let's just pull those things together. So that was ratios %194 minus 1, and then 1 over those ratios. And then list line plot. So that's telling us in this particular case, let's go ahead and fit that. A plus bx, abx. Okay, A is 0.3. Really? Okay, so let's take a look at that. So let's say plot. Let's just, for the hell of it, ignore the 0.67 there, and let's just say 0.3x, x0 to 150, and then let's say show that on top of %201. What did we goof up? What did we goof up here? This is, well, I'm just going to do the very naive fit. Length of %200, and then last %200, 0.67. Oh, silly me. I looked at the wrong thing. 0.6744. Okay, dandy. Now I just wonder how close that is to points to 2/3, whether it's basically consistent with 2/3 or whether it's excluded, whether 2/3 is excluded. Maybe consistent with 2/3. So if it is 2/3, that's saying that so if we unravel this back up, that's saying that the successive ratios, okay, so let's write this out. AN over AN minus 1, that's the ratios. 1 over that minus 1. Equals 2/3 N, let's say. Okay, so now let's see. I have no idea whether this will work, but we can try it. Okay, dandy. So that's the solution with an arbitrary constant for this. So let's take a look at what is this. If we say function expand, maybe this will give us something that isn't so pocked with pockhammers. Oh, great. Gamma functions instead. Let's see if we can do full simplify here. It's sitting with gamma functions. I think we can probably reduce those gamma functions to something. I thought that would, let me just see what that does. If I say function expand for that gamma function, let's say n an integer. Come on, there's a representation of that in terms of there's some gamma half integer type thing that should reduce this. How do I do that? I haven't used this function in a long time. I know we have this capability. Let's see also. Full simplify, target functions. All right, how do I do this? Without using any human knowledge of the gamma function. I thought function expand would do this. I'm really surprised it isn't. Why isn't function expand doing this? Well, let's just try this thing here with n declared to be an integer. No. All right. Let's get rid of that C1. I don't think that's doing anybody any good. And I doubt that the 8 pi whatchamajigamy is doing anybody much good. But let's just see a table of those things. N goes up to 10. What are those numbers? No idea. Well, the denominators are powers of 2. I can see that. Let's go ahead and pick up the denominator of those. And let's say log to the base 2 of that. Oh, great. 2, 3, 6, 9. Well, that wasn't such a hot idea because those denominators don't all okay, well, gamma of n plus 1. Boy, am I going to have to go look at I wonder whether I could feed this in. When in doubt, use another tool we have. Let's see whether this more heuristic animal is more capable of telling us something. Alternate form. Oh, well, that's interesting. Okay. Alternate form has that factorial. Approximate forms n to the... Okay. Now, an interesting question is, how do I copy that? Maybe I should use all of that stuff. Plain text. Okay. It's a little weird that that is. Is that a string? Okay, so that's telling us, oh, that's not very useful. That's just reducing the factorial. That's just saying that that thing is 5 plus 2n factorial. Okay, so we probably got a formula basically for that thing. And it's in terms of this factorial. So that's saying that that gamma function, if that is as a function of n, so if I plot that, let's make a let's say list plot of table of that thing. N goes up to 20, for example, 30 or something. Oh, I see. This is going to be the original thing. So this is going to go up. This is going to be the thing that increases exponentially. And then, oh boy, gets very big very quickly. But so if I take this thing and I take the ratios, so I take this thing divided by that thing for n minus 1, then I'm probably going to get, then I'm going to get the right thing. Okay, so that means each successive term is n plus 3 halves, which is exactly right. That's exactly what I would expect. Right, the ratios go up like n plus 3 halves. So in a first approximation, the final answer is on the order of n plus 3 halves to the n, which is kind of what I expect. Okay, so that's what that guy, n plus 3 halves to the n, is what that guy roughly goes like. Whether it's exactly that, okay. All right, so that's that one. The highly regular growth seems to be roughly 3 halves plus n to the n. So then there are these ones with larger scale growth, which have a different form. And then there's these ones with random eruptions. I mean, I have to say these random eruptions remind me, basically, I'm pretty sure that these things are, doing universal computation on their own. Okay, so let's pick one of these with I mean, I think these are going to just keep going with just really complicated stuff. Yeah, this ETIT is saying it's looked like big O for the halting problem. Yeah, I mean it's yes, this is a halting problem. This is, welcome to the world of undecidability. Will this go to 0 or not? It looks extremely implausible it's going to go to 0. What I'm guessing is that it is mostly just linear increase with these random fluctuations that basically can encode arbitrary computations. That's what I'm guessing is going on here. And if we take a look at some of these, I want to just look at what they do. And actually, we've done this ratios thing before, so we should just do that again. Actually, we can just copy this up here. Come on, we got a lot of crazy stuff going on here. Let's just copy this thing here. Exactly. And let's just use this. But let's increase the range here. So instead of 10,000, let's go to, let's live a little bit dangerously. Let's go to 100,000 and let's go to 4,000 steps here. See whether that can be done in a reasonable time. We'll find out. Yeah, Richard is saying it's like Rule 30 behavior in combinators. Yep, that's kind of what I expect. Oh boy. Okay. So these things, look at that creature. That is so frigging weird. Like, where are those eruptions? It also reminds me of the universal Turing machine that we found years ago, the very simple universal Turing machine. What's really interesting about this is, yeah, I mean, I'm quite certain that these things are representing essentially an arbitrary computation. We'll see what, how do we figure out, you know, the question is, can we encode these? You know, is there an equivalent Turing machine in which we can encode this behavior, so to speak? Can we prove that this thing is actually kind of, you know, Turing machine-like behavior? That's complicated. I mean, what I'd hoped to find here was that I can get sort of a baseline that explains why this thing keeps increasing in size, because then I can kind of remove that and look only at these kind of eruptions. I mean, it's also worth realizing that, well, let's take one of these. Let's take one of these guys that erupts, and let me look at something here. What I want to know is, if I look at the multi-way system, actually, I'm going to look at a couple of these. Let me look at this guy first. Let me look at this one here. This is the highly regular growth. Yeah, well, William is asking about the busy beaver problem. Yeah, I mean, that would be like finding one of these that goes on for a long time and goes crazy and then halts. And I found some that do things like that, and we can look, you know, at the longest kind of one that actually, I actually, let me just do a little busy beaver. Hold on, pin the busy beaver thing. We're going to get back to the busy beaver because I want to look at something there. Okay, so that's this guy here, and what I want to know from that one is what the multi-way combinator version of this is. Boring. So that means it's unique. It's got a unique sequence for the first 10 steps. 14 steps, it's got a unique sequence. Wow. Wow. Okay, is it going to branch? Is it not going to branch? It's still unique. 20 steps, still unique. Oh my gosh. I'm telling you, these creatures, every time you think you know what's going on, this is crazy. Okay. Wow. So what this is doing is, this is increasing in size rapidly at this rate, 3 halves plus n, but it's not branching. Okay. Is it going to branch? Wow. Wow. Well, that's really funky. So that says there's a unique, this combinator can only be rewritten in one way, but that way increases exponentially in size. So now I'm really curious what it actually looks like. Let's try looking at this. So let's try 10 steps, and then let's try, I don't know how to work this out, but actually I'm going to try the following. I'm going to say, what depth does it have? Well, that's very interesting. Okay, I'm about to learn what this is doing. Okay, so this is the depth. That means it's getting progressively bigger and bigger as a tree. So let's take a look here. This tree, okay, let's say 10 steps, and I wish I had a version of combinator tree that didn't have its silly labels on it. Okay, so this maybe is a very regular tree. What this seems to be doing is just increasing. What is this doing? I think it's just growing another branch on this tree at every step. Well, that's really nice. Okay, so we've got a permanently growing combinator that we can understand, more or less. By understand, I mean that in quotes somehow, because these things are not exactly easy to understand. But it looks like the thing has this bushy piece at the end, he says. Yeah, there's a little piece at the end, and then every previous tree, 1, 2, 3, 4, 1, 2, 3, 4, 5. I have this feeling that we can actually understand this guy. Let's take a look here. Let's go. In each of these, I have a possible idea. Depth slash at that thing. Okay, so my idea, which might be wrong. What? What the heck? Oh, confuzzled. Okay, let's take a look at these. Okay, so now what is this branch? This branch is an S of S of S of S of S of S of S, I think. So each one of these has a length, I claim. Oh, I'm so confused. Why is that? Oh, because it's a curried object. Never mind. Okay, we need a notion of an S length, which is how many arguments. So if I say, okay, so if I say function to application, I think it'll do the right thing. Is it going to do that? No, it's not. What I need to know is we don't really have a pattern construct for this. It's S of S blank of S blank of S blank with an arbitrary number of those pieces added. So how do I compute how many of those pieces there are? So I think what I have to do, it's the head of the head of the head of the head of the head. Okay, so I think I need to say, let's call it curry break, or curry, decurry in some sense. And that is of an expression. And what we're going to do is we're going to say, I think we're going to say nest list of the expression hold on. think what we're going to want to do is we're going to want to extrude pieces. So at each step, we want to take the first. Actually, I think this is an example of fold pair list, if I'm not mistaken. No, not quite. This is this sequence fold list? Ah, thank you. Somebody is pointing me to function repository. Is this helping? I think this is a different operation. Yeah, this is a different operation, slightly different operation. But let me look at the source notebook for this, because I'm curious whether this maybe has something relevant in it. Oh boy. That's wild. Nice code. Okay, let's see. Mano, maybe you can help here. I'm trying to unpack an object like this. So each step, actually, if what I did was just nest while list, X first, yeah, this might work. And then I say the test is head of hash is not equal to symbol. Okay, so let's say decurry of S of A, B, C. What?
What's the goal here again, Stephen?
I'm trying to turn this into a list S, comma A, comma B, comma C.
Okay.
Oh no, I know what I want to do here. I don't want to do that. I want to say head of that. Okay, and for each of those, then having done that, this is the right thing to do. Then I want to say, for each of those, I say first of that, and then I reverse that, I claim. Okay, and that first, when it doesn't get anything, it just does a nothing. Well, or it just does, I could just do a hash there. Okay, there we go, SABC. Okay, so there, let me just record this particular function here. Okay, so now what I'm claiming is if I do that, if I run this decurry thing across this thing, that I will see something interesting. I wonder if I'm right. Decurry across this. Oh my gosh. I'm telling you, these things are really hard to understand, which is perhaps why in 100 years people haven't understood them very well. Okay, I'm officially confused. Let's try running it a bit longer in case there's a transient at the beginning. Oh, ho, ho, look at that. Something very regular is going on. Okay, now we're getting somewhere. Okay, so that's showing us these subtrees, that what's happening is it's extruding the final subtree. It's basically just making a longer and longer and longer thing on that final subtree. And I think if we pick off that final subtree, which is otherwise known as, if we do decurry of first of hash, that final subtree is going to be the first there. And that's also very regular. Yeah, so this thing is making this very regular tree structure. So I think we just discovered that, wow, that's really quite interesting. I think somebody said it wasn't known whether there was an S thing that never branched. Well, now it is. And no doubt we can find a proof of that. Okay, so that's those ones. So now with this larger scale growth, let's try looking at one of those in the multi-way system. Okay, so let's look at that guy, and let's look at the multi-way evolution of that. I don't think we should do 50 steps. I think that's going to be a disaster. I think we should now do, let's be much more conservative here. I am confused. Come on, this one can't be a unique one as well. I'm now getting suspicious. All right, let's just check that we're not confusing ourselves here by something. Let's try one of these that's much less regular. Ah, okay, good. All right, now I feel better. Okay, so there's nothing. We're not making a mistake here. Wow, maybe these are unique as well. Let's take a look. That's really wild. Okay, let's do the same thing as we did here. Let's see whether they, I mean, because that one again was this, it's almost as if when it manages to grow this rapidly, it is, maxing itself out in some way that prevents it from doing anything wilder. Well, those look very, very regular. Very regular. Huh, okay, let's do this test now. Well, isn't that interesting? Okay. I bet this is very regular as well. Whenever you think you know what's going on, you don't. That's crazy. What the heck? What the heck is going on there? Okay, let's look at this guy for a couple more steps. Oh my gosh, I am really confused. So the first will be the right branch up there. That's the structure of that right branch tree. This is saying it's one, actually it's saying it's, not sure quite how to read these trees. So that branch there is the S. Oh yeah, that's the one. I think what's happening is that 135 is Yeah, I think these are tree depths for these things, and I think this isn't getting any deeper, it's just getting wider, I think. Let's just try running this for 30 steps. Oh gosh, I'm so confused again. Actually, I'm a little bit suspicious that 7 may not survive. So much for, I'm telling you, the general principle is computational animals are always smarter than you are. Look at this thing. What is this doing? What is this? This is crazy. 19. Is this some simple recurrence? How do we even tell? Looks like kind of random numbers, except that I wonder what permutations this is. It's 1, 1, 1. No, I don't understand it. Well, that's mildly interesting. Let me just try running it a few more steps. Oh no! Look at that! That's crazy! Look at that thing. I thought it was going to be periodic, but it's not. Okay, one more thing to look at. Okay, so larger scale growth up here. We had this. Where did I have it? We had 2 cases, so let's look at the other one. Just to see if it does the same thing. Now I'm probably going to blow my computer up because it's going to do something different, but let's try it anyway. Unique. Well, I am firmly confused. A theorem for somebody to prove. I don't know why that's unique. No idea. It's growing, yet it's unique. Okay, so let's look at the random eruption case. Okay, so in this case, I'm just going to do 10 steps. I'm going to do it on these cases here. And let's just see what these look like. Actually, what I want to do here is something. Let's do this. Okay. I'm going to do something. I want to see whether these are still growing or whether any of them reached fixed points. Oh, no, I know they can't have done. Never mind. Well, that's very interesting. They all seem to be identical. Let's find out if we do canonical graph. How long is it going to take to canonicalize those graphs? My gosh. Wow. Not that big graphs. Maybe it's hard to do this. I mean, in principle, you do k-factorial operations to canonicalize a graph. Well, those do look similar. So let's find out. Let's at least see. Let's just do the most obvious thing. Let's just look at the vertex counts. If those are different, we know they're different. Okay, all 210. Well, that's very interesting. You see, what's interesting is that these really have different structures, yet their multi-way graphs seem to be the same, which is really interesting. What does that mean? That means that the multi-way graph is the same. Okay, I need to show these in a different way. I've got an idea for how to do this. I have some code here that will show these in a more annotated way. Let's see. I think can do this. Actually, I need to look at something here. Yes. Okay, so this is actually going to show this, where it's going to show the leaf count of each of these things. So this thing here, so let's go here, 10. Oh, I should probably have done this in parallel. What is going on? Okay, now I'm even more confused. These, oh, I did something completely stupid here. Okay, guys, somebody should have noticed that. These are all different. I was just completely confused. Okay, what this is showing now, okay, so one of these actually was a unique one. The fourth one, 1, 2, 3, 4. Well, let's see if it stays unique. 10 steps is unique. Okay, let's go to 15 steps. Nope, it didn't stay unique. So those red things are places where the thing hasn't halted. Okay, so that's not going to stay unique. So in fact, I'm not as surprised as I was. These things all have different multi-way graph structures, which is kind of what I would have expected. So, and within these graph structures, the particular route that we were taking is one particular path through those graph structures. Now, there can also be graph structures. Okay, so another thing. So let's go back to busy beavers. And there are two kinds of busy beavers. One is something that runs a long time and then halts. And then we can kind of see that by looking at, okay, we had that SK terminated thing. And what I want to do is I want to say here. This was doing things that didn't terminate. So now what I want to do is I want to say things that do terminate. Let's say on length 7. And then let's say, I want to, find, okay, I want to find the length of that. No, I want to find, let's see, if SK terminated of hash, length of hash -1, otherwise nothing, or let's just say none. Apply that to this, and apply that thing to this groupings thing, and that's going to tell us what the halting time was. Oh, silly me. Okay, so those are the halting times together with the two that didn't halt. Okay, this is the halting times for length 7 ones. Okay, so that shows us the longest that doesn't halt takes 15 steps to not halt, to halt. Okay, so let's go up and try the 8 case. Okay, so let's say max of that. Oops. So this is going to be the busy beaver. Okay, so wow, that's 15 steps as well. So both at 7 and at 8, 15 steps is the maximum. And there are a bunch that we think don't halt based on the 2000 step criterion, which may not be the best criterion. We may have to go further to find the right criterion. So let's actually try going further, and let's say if they're going to halt, let's limit that at 5,000, and let's limit this at, let's say, 10,000 steps. Okay. I should. Okay, so now let's say max of that again. We're still at 15. So nothing more halted in this case. So let's go ahead and I'm actually curious now if I delete cases of this 287, none, and I make a histogram. Okay, so that's the halting time distribution for those things. Okay, let's keep going here. So let's say, so now remember, we might have missed a busy beaver. We might have missed a thing that busily works for a long time and then dies off, because one of these nuns might be incorrect. It might not, in fact, survive forever. And so let's call this halt 9 is this thing. And let's actually do this for real here. Well, that was fast. Okay, so let's say max of that. Okay, that's 86. So that's a thing that takes 86 steps but eventually halts. So now one thing I'm curious about is if I look at that 86 step creature, $433. Okay, so let's take that one. That's the relevant combinator. Okay, so let's say now let me do the multi-way combinator thing on that, because one thing I know about that is it eventually has to terminate, but it might take a while to do it. And let's see whether it bushes out before it terminates. Okay, so let's try 15 steps here. Oh gosh. Oh, this is interesting. Oh no, I'm going to kill my whole system. Oh no, it's dying. It just ran out of many gigabytes of memory. Splat. Oh well. Okay. Unfortunately, these creatures are very, they're very unruly. They go out of control very easily. Okay, let's try this. Let's try 4 steps. Boring. 6 steps. And this is just showing those are the leaves at the end. Let's say 7 steps. Okay. 8 steps. Okay, so notice that this looks like it's going to go on forever. 9 steps. But we know that after 86 steps, it actually terminates. So now I'm motivated to go back and look at some of these other ones and see what happens with these. So let's try this one here. And let's say the 15-step thing. Well, actually, let's just make the multi-way graphs for all of these. So assume that it terminated, and let's just try making all the multi-way graphs. I think I already did this, actually. Let me just look. Okay, so all multi-ways, all MWs for this. Okay. Let's say if sk terminated of sk fixed point evolve list, then make this thing here, and let's go for 15 steps, which may be more than enough. Let's not go for 15, let's go for 10 steps. And if it terminated, make that. Otherwise, just let's say none here. Okay, let's try this. I should run this in parallel. Oh, I should have said last of that. And what? Did I write the wrong test there? If sk terminated last of that, otherwise, graph of that. Oops. There is my mistake. Wait a minute. If sk terminated, oh, silly me. Okay. All right, and let me make this in parallel. Okay, so this is going to look at all the multi-way graphs, I hope. Come on. Come on. Wake up, computers. Oh, how can something like that happen again? Okay, these are the multi-way graphs. So there's a lot of multi-way graphs here. Well, this is quite interesting. So these are ones where there is a fixed point, but there is another path where the thing grows forever. And obviously I've got dumb sizing for those things. Okay, I'm gonna just try running it just for a little while longer. Let's just try running it for 2 more steps. This may be a horror, but anyway, let's just try it. Okay. So these heavy circles are the termination points. So this is a beaver that had, wasn't very busy. But this one here is interesting because this one here, let me just indicate what they actually are. Okay, so that one is interesting because it does terminate, but it has a path that doesn't terminate. Right, those red things don't terminate, but it can get to the termination point. But let's see whether any of the other do that. Okay, so let's look at those two which have a termination point, but where they seem to have ways to go astray. Okay, so let's look at that one there. If I could only select it, I should have set it up differently. Come on. Okay. Okay, so these are ones where I'm just curious whether those actually are the long running ones, but let's take a look here. So this, Let's try running it 13 steps, see whether it'll be a disaster. Okay. Okay, so that's running. The sizes of these things are just the number. I should have had it auto scale. Their sizes are based on the number of, okay, so let's go to 15 steps. Oh, interesting. So this is a busy beaver. This went for 15 steps and then everything terminated. It reached termination on every path. There was no possibility, there was no path where it could get lost, but then it still terminated. So let's take a look at this guy here, see whether that has the same property, that it sort of stays hot for a while. And then, I mean, the question is, can you have an event horizon? Can you have something where some part of it, I mean, we know in these systems there's causal invariance. So if it terminates, there must be a unique termination point. So it has the Church-Rosser property. That one terminates as well. So both of those have the feature that they run for a while and then they terminate, but they always terminate. So now the question would be, if we go for size 8, let me just do this, but I'm going to make it smaller because I don't want to see such a big mess here. Let's go up here. I'm going to do this. I really should have set this up to not make such giant things. It's kind of dumb, but anyway. Okay, let's do this here. Graph of that, arrow this. And then I'm not going to worry about the nail. Let's do the nuns like that. And then let's say interactive list selector. Okay, and I want to do an 8 there. Now I think I'm going to go back to a 10 there and just take a look at what happens. Okay, ready? Here goes. Come on, come on, come on, computer. Okay, all right, so some terminate. There's a terminator. That one is still active. All right, let's just select the ones that are still active. So a lot of them just terminate. These are ones where the, I don't know why this is taking so long to select, but anyway, okay. That's weird. That's in the middle of the pack. It looks active, but it looks like it died at the end. Okay, this is getting boring, selecting these. But these are, so each one of these is, I should have programmatically done this. Obviously, I could do that programmatically. And next time I'm going to do it programmatically because this is dumb. Okay, copy those, paste them. Okay, there they are. Okay, let's go back up to the top here and let's try running those a little bit longer, see whether they resolve. So, yeah, take this thing. Okay, let's try running just 12 steps. I don't want to go push my luck too much. Okay, one of them resolved. All right, great. So now the question is, are they all going to resolve? Let's go to 14 steps. Interesting. Okay, so maybe there's a theorem that says with these S things that if it's going to resolve, he says, okay, let's just go to 16 steps and see whether that one resolves. Yes, it does. So all of those resolve. So there's nothing where there's an event horizon where one set of things resolve but the others don't. Okay, that makes me want to go and look at the 9 case and check that. Where is it? Okay, so in this case here, what I want to do is, well, I can just do the 9 case, but I don't want to be looking at them all. So actually what I want to do, let's at least do this. Let's do the following. Is SK terminated? Okay, I have an idea here. Maybe what we should do is to say in here, take largest by on this by vertex count. What's the order of arguments to take largest by? F comma n, I thought so. Okay, so let's just take the 10 largest by vertex count and just see what we would get in this case. What? What? That's crazy. Okay. Oh, I know what's wrong. Vertex count of first of hash. That's not encouraging. Okay, what did I get wrong here? This is giving me a list of the form something arrow the combinator. So let's just go here. Let's just do that for 6. Okay, so those are graphs. So I want to say vertex count of first of hash. That gives vertex counts. Actually, that's quite useful on its own right. That's the, okay, that's the vertex count. I'm very confused here. So now I don't understand why this doesn't give me I want to say take largest by that thing, comma, vertex count of first of that, comma, 5 or something. Well, maybe those are the largest vertex counts. Okay, fine. So let's go to size 7 then. And they should be, what is that? Why is it doing that? You know what? I'm going to do this. That's why it's doing this. It's because I need to do a delete cases on this. SK terminated. Okay, here we go. So these are now the ones that are the most unresolved after 10 steps with size 7. Okay, so now, and this one should resolve, we think after 15 steps, that one all resolves. Okay, great. Okay, so now let's let's say 15 steps, size 8. Okay, so these are the busiest of the beavers, and they've all resolved at size. Well, we probably should go a little bit further. We should go 10 of these. Okay, great. Now let's go the 9 case. Maybe I ran it too long. Maybe the 15 is too long. Let's hope for the best. Sometimes when you run these parallel computations, it's the counter is telling you about the ones that are really long running. So if we're lucky, it will speed up, because it's right now it's running. It doesn't know how many it's done because it's been stuck doing some of the really. I was right. It ran through the others very fast. So there were just a few long running ones, and then the others were very fast. Now this is a bad sign, because now it's sending data back from the parallel nodes, and it's taking a very long time to do it, which suggests that there are some giant graphs here. But let's see what happens. Okay, we know it computed it, at least unless something went horribly wrong. It successfully computed all these results. Okay, something's spinning. That's always maybe a good sign, maybe a bad sign. It's probably it's sending back some vast amount of data, because one of those graphs was absolutely huge. Wow. Well, that's interesting. That is probably because I should have set these graphs to not be as persnickety in how they place the arrows. I think there's something that's being dynamically done to place arrows, which is probably completely bonkers if the graph is too big. I have never seen that in this situation. Let's see what happens. I think this is probably a bad news. Yeah, okay. Let's not live as dangerously as that. Let's go to this, and let's okay. Splatteroo. Okay. Dynamic updating enabled. Hopefully the parallel kernels that were controlled by this machine all died off. I think that's been much improved recently. The ability of a parallel kernel to know that its controller is dead. Okay, here we go. This is going at a nice zippy speed. That's encouraging. Nothing absolutely crazy probably has happened, he says, optimistically. Why is this taking forever? What is it doing? What is going on? How can these graphs be that big, he says. I'm telling you, you've got to remember that computational animals are always smarter than you are. Something has done something really bizarre and crazy and huge here that we didn't expect. But let's hope for, oh, there we go. Okay, so what these are, which is quite interesting, is these are all ones which we know terminate, but they're still active at this stage. So in other words, we don't know if this final tree is finite, or whether, let's pick one of the slightly more modest ones. Let's pick this one here. If I can only select it, I should have set this up differently. Okay, let's pick that one there. And let's simply say, oh, that wasn't good. Okay, let's pick, yes, Amdahl's law is biting us. All these things are very, unfortunately, I have a fairly, I could run this on a cloud, on AWS or something. I could send off a batch job, but I think, there's a trade-off, because if I do that, I'm not going to get the results back immediately. And so it's better most of the time. Okay, there we go. All right, so let's see if that guy, let's see what happens to that one. So that's at 12 steps. Let's see whether it resolves to terminate, because we know it does terminate. Let's see how long that one actually takes to terminate. So we know that it had terminated by that point. So let's just see what the termination time is for this one. Oh boy. You know, this is a crazy world. This thing gets to size 40 and then it doesn't actually terminate. It's the expression is changing, but the thing is, okay, so let's look at the length there. So after 30 steps, we know this thing at least has one path that terminates. So let's see how dangerously we want to live on this one. Let's go to 15 here. Oh boy. No. Oh, look at that. Look at that. That is a termination spot. That dark black thing is a place where it terminated. Okay, so the question is all of this going to terminate? So this is kind of a multi-way busy beaver. This is something which is going to terminate in not that many steps, 30 steps. But the question is, okay, do we really want to do this? Is this going to just blow up the machine? It may do. I think I have like nearly 1 terabyte of RAM in this machine, so it can go a long way. This is a very busy creature. So remember, this is all the parallel paths it can follow, but we know it is able to reach that spot there, which is a termination spot. If it reaches that spot, it's done. But different evaluation orders, essentially different reference frames, give you different ways of sorting through this graph. And wow, that's kind of a cool graph actually, because this is showing at each level, it's showing all these states, and these are states that are still open. And now this is saying there is a path, leftmost, outermost will bring us on a path down here that will hit that point. But these other evaluation schemes will go flapping around all over the place. Well, this may not terminate. I mean, in reasonable time. Oh, it's doing something. Oh, let's see what's happening. Something's coming back. It's either going to die or not. Oh no, that was just a spinning disk for saving the file. No fun. All right, let's kill this off. This is not promising. Great, it's killing my whole system. Okay, so the basic conclusion is there can be these very large structures which still maybe always lead to termination. So that makes me wonder, so this is kind of the busy beaver, multi-way busy beavers, a new concept, just one of many, but that's a, okay, so these are, so I'm kind of it makes me wonder whether I should look at things. Let's just say we go to, let's say 10 steps, and let's go down here. Let's get the top 30 of those. So that's going to, because I want to find one where we can actually see the whole sort of busy beaver-like thing, even though, I mean, each of these we know will eventually terminate. In fact, I think there's a termination spot there. Oh yeah, these actually show termination spots. They just are still alive in terms of everything else. And we don't know whether there's an infinite branch or whether everything will eventually terminate on that finite branch. That's unknown. And that's okay, let's see what the top 30 look like. Almost time for me to go get my dinner here, but okay, so here are a bunch which are terminating. So these are ones which get quite big but do terminate. And you see, I'm on a hunt for one that basically has a termination, but also has a path that doesn't terminate. And I'm kind of wondering if this guy might be an example of that. We will see. Okay, that was what we had before. Let's go to 12 steps. It's dying out. It's going to all terminate. It's going to die out. Splat. It all died out. So what we didn't have is something where because I found those, at least I think I found that in the case of, in fact, I now feel like I want to check that. Let's see. Yeah, I want to check this. I found one that I think is of that type. Hold on. Just want to check this here. This is one with a K combinator as well, where I think at, let's say, 15 steps. Oops. Okay, so that's got termination, and it's also got things that are growing unterminated. Okay, so let's go to 16 steps, and it's getting more unterminated stuff. And so the claim is that the unterminated things are growing in number. And it's not going to, it's just going to increase the number of unterminated things. And I think if we go through here and we just ask for just do this, and we say like 15 steps, and then we say count by, oh, that's not a thing. We should have that. SK terminated of to expression of that, and then I want to map that at level 2, and then I want to say there count hash comma count hash comma true, count hash comma false. And then I want to do that against that. Okay, let's see how that works. Okay, so that's the number of all the expressions generated, how many correspond to okay, so this is showing how the number of unterminated ones increases. This is actually a good I'm just going to make a separate note of this. This is SK branched termination. It's its own separate thing. And this is showing that this really isn't going to terminate because this thing is growing rapidly. Its number of its number of unterminated. It's got one terminated thing, but its number of unterminated ones is increasing rapidly. So let's compare that with one of the guys up here. Well, for example, that first one there, that we had trouble with before. And let's see whether we believe that it's going to, in fact, terminate, or whether, whether it's, because we know this one terminates. We know this one has a termination path. And that's growing pretty rapidly. So it got to its termination point. See if we can go in a few more steps. Dangerous, dangerous. Is this going to crash? Come on. We at least get a few more steps here. Okay. I don't think that's going to terminate. I think that's, well, let's take a look at the you know, these things are really strange. I doubt that's going to terminate, but who knows? All right, well, I think we're beginning to, I'm not sure what else we're going to be able to figure out here, although I would love to figure out yeah, I mean, okay, so what we've learned here, okay, this is kind of interesting that there's one in here that appears to not go to unique state, that appears that there are updating rules that just lead it off into la-la land. Even if, actually, let's see, we can look at that because we have a different updating rule. Okay, so this one, let's see if I have a code for this here immediately. Let's see. Now let's just do this. Nest list of sk first position, sk evolve, no, sk step first position. That is just doing a different updating scheme. And then we can say here, wherever it was, this thing here, and then we say leaf count. So if I just do sk step here, then after this gets, say, 30 steps, boom, it reached constant. Okay. Now let's do the corresponding thing for step first position here. Let's go 20 steps there. It also manages to terminate. So in other words, the evaluation strategy that makes it not terminate is something wilder than those two. So those two both lead to termination. So in that plot that we had up there, where it's got all kinds of non-terminating pieces, the strategy that leads to non-termination has to be something more complicated than those. So one thing we could do is to look at a strategy. Well, okay, so let's do the following. Let's do this. Let's say we look at these steps, and then we ask for each of those SK matches in each of those. So that's going to show me what the positions are at which things match. And so the point is that some of those positions, if we followed some of those positions, we would be off in la la land, basically. So let me see. One thing we could do here is take this and let's just try a different evaluation strategy in which we use /dot, which will do multiple rules at the same time. Let's see what that does. Oh my gosh, that goes to 115 in a very small number of steps. So the question then is, what is it that's leading the thing to not terminate? What is a path that's leading to non-termination? So let's do the following. Let's ask it. Let's say the following. Okay, so this is the thing. And let's now just, oh boy, how to get this? I'm trying to find a path through here. Oh boy. Let's try doing the following. Let's just try making graph. I wonder if this will work. I don't know if this will work. Let's just do 10 steps. Oh. Oh my gosh. Okay, well, here. Leaf count. All right, so that's simply labeling what the heck? What is going on here? I am very confused. Okay, so this is the multi-rate combinator thing. Well, let's do the following here at least. What's it going wrong? I've done something stupid here. Oh, I know what I've probably done. Vertex labels. I don't know what I did wrong here. Let's take a look. Why did they all say 115? That's a very bad sign. Vertex list of G. Mapping of a vertex list of G, this leaf count. Well, let's echo that whole thing. Oh, I see what's wrong. Silly me. I need to say hash arrow, that leaf count. Okay. 10 steps. All right. So this is now showing us how big, God, hard to interpret. Okay, how big the leaf count is Okay, so there's the 115, which is the known endpoint. So what we're trying to understand here is what path is going to lead us into La La Land and never get to 115? Or is that not going to happen? And I mean, I would have expected that these numbers would have gotten much bigger and that they would be, let's see, how are we going to do this? Wow. Well, actually, one thing we could do is something simpler here, which is just to do this and to say here, 13 steps. And now let's ask, what is the leaf count of two expression hash that mapping this okay, so what this should do, if it all went according to plan, is this should generate the set of expressions at each level. Here we go. I'm a little suspicious here. I'm going to try one more step, maybe a big mistake. So this is saying how many expressions are there in our attempt. I mean, what we're asking is, does everything go to the 115? Or are there things that get lost and go off forever? Well, it's maybe a mistake here, but what I'm concluding, looking at this, that's the 115. That's the one that's the thing up there. That's the end. That's what, when they terminate, they get to that point there, presumably. And what's strange is that there aren't intermediate expressions which are bigger, because usually what ends up happening is that there are sort of big intermediate expressions generated. This, it just looks like it's kind of dumb and it's not getting there. It's not like it went off into La La Land and found things that were, you know, way bigger and which are never going to converge back to 115 again. Yeah, Richard is saying 1 over square root of length is the empirical halting probability, at least in von Neumann programs. I don't believe that claim. I don't believe that claim. I mean, maybe that claim is true for some register machine. I don't believe that claim. I think that let me think about that for a second. I mean, that's kind of a random walk belief about halting, but I don't think that's really how it works. Well, I think we should probably wrap up soon here. Thank you all for joining me for this combinatory frolicking with the combinatory animals. There, look, it's almost a combinatory duck or something. It's lost its head, but whatever. You know, what's just amazing, these things are 100 years old and we don't know all this stuff. You know, we've discovered some things in this live stream that weren't known, at least not to me, and I don't think to anybody before. That's cool. The one thing I was really hoping to get is a way of understanding, of proving the non-halting of like that length size 7 S combinator expression. I also would like to understand yeah, I mean, I think right. I mean, I'm really confused by the fact that we can't find an explicit strategy that causes this one to get lost, and maybe there isn't one. Maybe, and it might be the case that for S combinator expressions alone, they either have to terminate or they have to go on forever. But anyway, I think oh, this is Richard is saying that this thing about 1/square root of length is based on actual machine code execution of actual random programs. Yeah, it's an interesting thing. I tried doing that actually years ago. And when I was working on the NKS book, I tried taking random Wolfram language programs, but I also tried taking random assembly language programs and seeing how long they took to halt. And they basically they got core dumps, they got seg faults fairly quickly most of the time. All right. Well, until another time. We've got until December 7th to figure out some good things about combinators, because that's when I'm thinking of doing some kind of combinator celebration week that week. If we have enough to say about combinators, we'll have a combinator celebration week. And hopefully by that time, I've been trying to research the personal history of Moses Schoenfinkel, the inventor of combinators, which unfortunately is probably not a happy history, but one where we're gradually finding more information. We've had a few breakthroughs in finding some surprisingly good information from some surprisingly obscure records, but we still have a lot of mysteries and a lot of how on earth did he come up with this stuff at that time. And I think combinators have had more of an influence on the history of computation than people understand. I mean, they were the precursor of lambda calculus. And for example, somebody like me in designing sort of the early ideas for Wolfram language basically went back to combinator type ideas. And really every idea from combinators has found a place but one. And the one is never name variables. We don't have that idea that idea is not an idea that us humans seem to be able to deal with very well. And that's, although I'm sort of wondering whether if you were sort of programming, I wonder whether if you were programming sort of more graphically, yeah, I don't think it really helps you very much, because it's kind of like you can have, in Wolfram language, you have hash, but you can imagine, multiple genders of pronouns, so to speak, where the hash refers to different things. But honestly, that doesn't really help you. You might as well name variables at that point. But the idea of combinators where you just can flow the data around without naming variables just doesn't seem to be something that we humans understand very well. All right, well, we should wrap it up there. So thank you all very much, and see you another time. Thanks.